Hello and welcome to this lecture. We're going to be talking about general random variables and in particular continuous random variables. So let's do a quick recap of where we are with respect to random variables. We saw discrete random variables. So what are discrete random variables? We looked at a probability space where the outcomes, the sample space which contains all the outcomes is actually a discrete set, right? It's not doesn't have an interval of the real line, for instance. It's a discrete set. And we looked at definition of events in that sample space, which is probably all possible subsets, etc., things like that. And then we looked at assigning probabilities to events. Now, how did we assign probabilities to events? We eventually came to this idea of PMF for discrete random variables, which seemed like a very easy and simple way to assign probabilities to every outcome, and then that in turn gave you probabilities to every event, and we are very comfortable with that setup. So then when this week we've been talking about situations where the discrete random variable, even though the actual set is discrete, the number of such outcomes is so large, or it comes to a situation where dealing with the discrete PMF seems to be very painful. It's not very easy to count and see how many, what's the probability, etc. And it seems like going to the CDF and in particular doing an approximation of the discrete CDF with the continuous CDF seems to be a very good idea. Okay, but the discrete CDF came from an actual probability space, right? So there was a probability space where there were outcomes, there were events and the PMF, and then we got the CDF. Where does the continuous CDF come from? Does it come from a probability space, right? So that's a question that one might ask. It turns out answering that question is very technically painful. Okay, so it's not, maybe today it's not that involved, but if you start reading it on your own when you're starting out, it's a very painful technical journey to understand all that. So what we'll do is we'll sort of accept the continuous CDF as corresponding to a random variable and start studying what kind of random variable it is, how to deal with that, etc. So that brings us into this wonderful possibility of general random variables, continuous random variables. We won't talk about the probability space and all too much, even though it'll be sort of intuitive that there should be something like that, and it's not too difficult to imagine. It shows up some, so this kind of thing throws up something unusual. I'll point that out as well. But this is a very interesting new type of random variable that we're going to study in this lecture. Okay, not discrete, but continuous random variable, different type of random variable, which has very interesting new properties. Okay, and it's very useful in modeling. Hopefully, you're convinced of that based on the examples I gave you. How when you model real scenarios, there are many scenarios where you don't want to be restricted by the discrete world in some sense, right? So it's sort of, it seems too painful, and anyway, the continuous approximation is very nice and easy to deal with. And let's explore what that means from a random variable point of view in this lecture. So this theorem basically allows us to define a CDF first, a valid CDF. You can define in any which way you like. You can just take a pencil and draw a line from 0 to 1, and this theorem sort of assures you that there is a random variable in some probability space, etc., etc., and you don't have to worry about it. Just deal with the random variable as if it were already known to you. Notice the connection between the CDF that you came up with and the random variable. The value of the CDF at a particular value input x, small x, f of x, is actually the probability that this random variable is less than or equal to that small x. Okay, so that connection is very, very important, and that allows us to use the CDF directly to compute probabilities involving the random variable. Any event you define using the random variable, right? X falls inside an interval, x is greater than something, x is less than something. You can use this connection to derive all those probabilities. Okay, so what is the main relationship here? Here is the main relationship. Well, the main relationship is given in the theorem itself. So one of the quick properties you can derive using this relationship is that probability that x falls between a and b, right? Note that you have a is less than and then b is less than or equal to. That is important. Okay, and that is f of b minus f of a. You can see why that is true. See, f of b, maybe I should write something here. F of b is probability that x is less than or equal to b. F of a is probability that x is less than or equal to a. If you subtract these two guys, what are you going to get? X has to be strictly greater than a, but it needs to be less than or equal to b, right? So this is the difference. It's basic events, right? So event, if you subtract, so x less than or equal to a is contained in the event x less than or equal to b. So if you subtract the two probabilities, you're going to get the probability that x falls between, strictly greater than a, but less than or equal to b. Okay, so it's a nice simple property. So once you come up with a CDF, once it's valid, you can find any probability you want for involving the random variable. That's very important. Now there's a couple of critical things to worry about. Now, what is the probability that x equal to small x, right? So we've got intervals, we've got less than or equal to. How do you find the probability that capital X is equal to a? Equal to a. That's just one single event, right? If you remember the PMF, that played an important role. The PMF was pretty much probability that x equal to a particular value, right? But here we are not talking entirely about x taking a particular value. We are only saying less than or equal to, less than, greater than. What about probability that x equal to a particular value? Now that is the point where these continuous random variables, arbitrary CDFs, they differ sharply from discrete random variables. So let me emphasize that a little bit by talking about that point. So if you remember the CDF can have jumps, right? Particularly for discrete random variables, we see that it's flat jump, flat jump, flat jump, like that. That's how it proceeds. But for continuous random variables, we allow for a continuous line also, but also for a continuous CDF, CDF can be continuous, but also it can have jumps. Jumps are not disallowed. So CDF has to start at 0. It has to keep increasing. It cannot decrease. It has to increase all the way to 1. It can increase either by jump or slowly, steadily, like in a continuous manner, it can increase, right? So now, if the CDF that you drew rose at one particular point, x1, it had a jump from f1 to f2, then the probability that x equals that value x1, the value at which the jump occurs, that probability is f2 minus f1, just the width of the jump. I'll show you an example soon enough, you'll see what I mean. So if there is a jump in the PDF, then a probability that x equal to that value is the magnitude of the jump, how much you jumped by, right? You can only jump up, you can't jump down as you go, right? It's an increasing function, okay? So that's the first result about probability that x taking a particular value, right? X falling between two values, just difference, you know how to do it. But what about x equal to a particular value? If there is a jump, it's equal to the magnitude of the jump. Now, the next natural question is, what if there is no jump, right? So if f of x is continuous at a point x0, there is no jump at x0, then the probability that x equal to x0 is equal to 0. Okay, so this is a bit non-intuitive. A lot of people get a bit confused by that. I'll tell you why the confusion comes soon enough in the next page, but this is an important point to remember. So these three properties sort of you should remember for a CDF. Suppose somebody gives you a CDF and wants you to identify the probabilities for intervals, what should you do? Probability of a particular point, what should you do? If there is a jump, probability that x takes a particular value of that at that point is the magnitude of the jump. If there is no jump, probability that x equal to that value is 0. And if you are given an interval, it is simply f of b minus f of a. Okay. So now why is this non-intuitive? Why is this, when f is continuous, the probability that x equal to x0 being 0, why is that non-intuitive? Here is the reason why. So let me take an example and then talk about what happens. Okay. So here is an example of a random variable x with some CDF f of x, and that f of x is drawn for you here. Okay. So this is f of x versus x. Okay. So that's the picture that we have here. Okay. So you can see it starts at 0, right? So it starts at 0, it keeps going, it stays at 0 till 0. At 0, there is a jump. Okay, so at 0, there is a jump. Okay, and what's the magnitude of the jump? The magnitude of the jump is 0.5. Okay, you can quickly see, even from this definition, you can see for x strictly less than 0, it's 0. For x equal to 0, it's 0.5, right? It has jumped up by 0.5. After that, there's no jump. It's just 0.5 plus 0.1x. So that at 5, so this point is 5, for instance. maybe this is not marked here. So at 5 it reaches 1 and stays 1 afterwards, right? So this is just that line. This line is 0.5 plus 0.1x. Okay, so you can see why this is a valid CDF. Every property of the CDF is satisfied. There is a jump here though. Okay, so now notice what happens if you start looking at calculating probabilities using this CDF. So there's a random variable with this CDF. Now I'm going to throw some intervals at you, throw some values at you, and we're going to try and compute probabilities. The first value you can compute probability for is the probability that x equal to 0. That's 0.5, right? So I just drew the magnitude of the jump, and you can see that at 0 there is a jump of 0.5. So probability that x equal to 0 is 0.5. It's easy enough to see. Okay. Now notice what happens when I look at an interval around 2. So this 1.99 and 2.01 are somewhere here, right? So this interval, I'm going to take small intervals around 2, around the point 2. Okay. So what's the probability that x falls between 1.99 and 2.01? Okay, so you notice how I put strictly less than here and less than or equal to here. This is an interval, so I can just do f of 2.01 minus f of 1.99. So that is just, if you plug that in here, you will get 0.1 times 2.01 minus 1.99. That's 0.1 times 0.02. That's 0.002. Okay, there is a small probability because this interval has a small width. It's not very high. So this probability is small, but it's non-zero. There is a non-zero probability that x falls in the interval 1.99 and 2.01. Okay, so that's all right. You get small probability. Now, if you make if you have a finite precision for your random variable x, it is taken with positive probability. Okay, so that seems fine. Now what happens when you increase the precision, when you make the precision higher, right? So you say x has to be between 1.99999 and 2.00001. You're making the width of the interval smaller, then the probability keeps falling. Okay, so the probability that it's within an interval is non-zero, but as you keep decreasing the width, clearly the probability keeps on falling. Okay, so now it turns out if you keep pushing and pushing and pushing in the limit, okay, if you say probability that x equals 2.00000 with no limit on precision, then the answer has to be equal to 0. Okay, so this is what is non-intuitive about it, right? So 2, the value 2 is actually in the interval 1.99 to 2.01. Is that okay? Now x can take a value in the interval with probability 0.002, but the probability that x takes any value in the interval equal to 2.000 with infinite precision is actually 0. We don't associate a positive probability with values taken in the interval. Okay, so this is one confusing thing in the theory. It would have been nice to not have this, maybe something else, but it turns out to have a consistent theory, you have to do this with continuous this kind of CDFs and random variables defined from the CDF. In the discrete probability case, we never had such confusion, right? So it's very clear what the values taken by the random variable are. So in the continuous case, the random variables take values sort of which are in intervals. With some intervals, you can say something. With lesser precision, you can say something. Okay, with infinite precision, you can never really nail down any continuous random variable or place where the CDF is continuous. You cannot really nail it down with infinite precision. That's not allowed. It's just not possible. You have to say 0, right, once you go to infinite precision. So this confuses people a lot. Everybody gets confused by this. It cannot take any value. You're saying it cannot take. I'm not saying it cannot take any value. It can take some value, but you can't be so precise about the value. You're not allowed to go to arbitrary levels of precision. That's all. Okay. So I mean, take it with a pinch of salt. If you don't want to understand it too much, you can just forget about it. You can just say the CDF defines a random variable, and that random variable's probabilities are calculated like this. Where the CDF is continuous, the random variable at that point with infinite precision, it takes that value with probability 0. But if you go around that point, it has a non-zero probability of falling in that interval. Okay, so that's the best way You can think about it. The foundations of this, why this is so, is very deep in the technical nature of the mathematical theory. I'll point you to some literature maybe later on if you're interested. Okay. So this is the main result here. You cannot take values with infinite precision when f of x is continuous at that point. Okay. So let's just accept it for now, and we will use this rule very clearly, right? If f of x jumps at a point, then it takes that value with non-zero probability. If it is not jumping, okay, it is just smooth and continuous at that point, it takes that value with probability 0. So for instance, if somebody says in this CDF, what's the probability that x equals 4? You should just say 0. Okay. But what's the probability that x lies between 3.9 and 4.1? You have to say 0.02. Okay. So that's it's a little bit unsettling, but that's what it is. When you are imprecise, you can put a non-zero probability. When you're very, very precise down to the last infinite precision, it's just impossible. You can't assign proper probabilities there. Okay. So I'll stop here for this, but think about this. This is just remember this as a method to go from CDF to probabilities for a random variable. Okay. So now we come to the definition of a continuous random variable. So so far we have talked about discrete random variables, CDFs for discrete random variables, and then we saw that this notion of a CDF can be generalized. I can think of a continuous function maybe even, which is a valid CDF, and then we said for every valid CDF there is a random variable. Now we come to a condition on the CDF which will make your random variable itself continuous. Okay, so that is this definition. A random variable which has with a CDF fx of x is said to be continuous if the CDF function is continuous at every point. There are no jumps. If there are no jumps, right? So previously, just the example we saw, there was a jump and then there was no jump. Now, what if the entire CDF has no jumps? Then it becomes a pure continuous random variable. Okay, so that's the idea. So I mean, it's a bit bizarre, but that's the nature of it. There are no jumps in the CDF. So what happens to probability that x equals x? It's 0 for every x. If you specify small x with exact precision and you want your x to be exactly that, it is 0. But around that, you can assign a non-zero probability. Okay, it falls into an interval, is f of b minus f of a. But notice, when in this interval, we had this confusing thing of I have to say a strictly less than x, less than or equal to b. I have to keep saying that for a given a CDF, because there may be jumps. Now, if there are no jumps in the PDF, notice what happens. Probability that x equal to a is 0. Probability that x equal to b is 0. So what happens because of that is all these limits don't matter. The intervals less than or equal to doesn't matter, because probability that x equal to a is 0. So I can just drop the less than or equal to and less than and simply have equality here for all possible intervals, whether they are closed on one side, open on one side, closed on both sides, open on both sides. All of them have the same probability. So that's a very nice, comforting thing about continuous random variable. Of course, the one that makes everybody uncomfortable is it never takes any one value, exact precise value with positive probability, but it can take values in an interval. So it's sort of like, that's how continuous things are. They're always like that. Okay. So this is one slide which defines continuous random variables. But remember the last point. So when you're dealing with continuous random variables or a range where the random variable is continuous, you don't have to worry about less than or equal to less than. All of them have the same probability. But if there are jumps, then you have to worry about this less than or equal to. Okay. All right. So let's now look at a few examples. Okay. So here are a few examples. So given a CDF, one of the skills that you need to pick up, if somebody draws a picture of the CDF and shows it to you, you should be able to identify whether it is discrete or whether it is continuous or if it is neither. Okay. So I have 4 examples here of CDFs. All of them are valid CDFs. So of course, the first skill is to identify whether or not it's a valid CDF, right? Valid CDF, you know the conditions. It has to start at 0 and then it can jump or not jump, but it has to keep increasing. At least non-decreasing, and then finally hit 1 and then it stays flat. There is that right continuity condition, but it's okay. I think it's a technical condition, but this is the CDF definition. But according to those definitions, all these 4 are valid CDFs. You can see the top left is a discrete random variable, right? How do you identify the discrete random variable? It will only have jumps. It will not increase without a jump. Every increase will be at a jump. It will jump or stay flat, jump or stay flat, jump or stay flat. If it does like that, then it's discrete. How do you identify the values taken by a discrete random variable? You go look at the CDF, wherever it jumps, those values the random variable takes. And what is the probability with which it takes those values? The magnitude of the jump. Okay, so if you look at the top left, it takes values 1, 2, 3, 4, 5, 6, each with probability it looks like 1 by 6, right? So it's like a throw of the die, right? On the other hand, let's look at the top right, which is clearly a continuous random variable. This CDF has no jumps. It starts at 0 and then goes in a straight line to 1 and it's flat after that. It's a continuous random variable. If you want to calculate probability that it takes one particular value, it's always 0. But if it falls within the interval, you just have to subtract from top to the other. So for instance, this random variable probability that it falls in the interval 0 to 6 is actually 1, right? The top right, that's it. It falls entirely in that interval. What values it takes, if you want to take 2 to 4, you can subtract it out. You'll see 1 by 3 is the probability, 0 to 3 is 1 by 2. You can sort of calculate based on this equation. Okay, so that's the top right. Now the bottom left is a mixture. Okay, it's neither continuous nor discrete because it does both. It has a jump and it also rises without a jump in a continuous fashion to 1. Okay, so that's a mixture distribution. It's neither discrete nor continuous. Okay, so there are cases like that. Rarely we will see such cases also, but mostly we will either consider discrete or continuous random variable. Yet another example at the bottom right of a continuous random variable is like a smooth curve. It need not just be lines, right? It can have a smooth curve that increases from 0 to 1. That's again a continuous random variable. There are no jumps here, but the probability of intervals is a bit different from what we had before, right? So it looks like the way the curve is drawn, it takes a lot of values and all that. So I mean, we don't have precise equation here, so we need the precise equation of the curve to say anything more, but clearly one can identify it's a continuous random variable. Okay, so this is a good skill, and you should clearly know that. Seeing a picture of a PDF, a CDF, identify whether it represents a discrete random variable or a continuous random variable or a mixture, which is neither discrete nor continuous. Okay, all right. So that's hopefully this gives you some idea of how these random variables with a general CDF may look. Okay. So where would you use continuous models? So I'm going to throw a few scenarios at you where the number of values that are taken in that random phenomenon is such that discrete may not really be very useful for you. You may want to use a continuous random variable to approximate situation. Okay. So here's the first situation. It's a very standard example in many books. This is given as an example. You have a dart which you're throwing into a circular board, and you want to measure the distance from the center of the board to the dart. Okay, so it's a very standard example that's given to say why you may need continuous random variables. It can fall all over. There are so many distances depending on how precisely you measure. You will get so many different possibilities. Dealing with discrete will be very tough. Continuous might be easy. Weight of a meteorite hitting Earth, we already saw that example. We saw there so many values, and continuous was so much more easier to deal with. Weight of a human being, height of a human being. There's such a wide variety of heights that you might as well deal with a continuous random variable and do calculations. Coming back to cricket, we've been talking about cricket a lot. The bowling speed, the speed of a delivery in cricket, that's probably a good thing. Think of a random variable. Price of a stock, because the stock keeps varying over a wide lot of different values it takes. Keeping track of the discrete nature may not be that easy. Continuous might be much more easy. Okay, so hopefully, I mean, so this is something you have to look out for when some data comes to you. Which is the data that you want to sort of model with a discrete random variable, which you want to model with a continuous one, which is well modeled like that, which maybe you may even have to use mixtures, right? So for which you may have to use mixtures, things like that. You have to identify that. That's good to do. And these are the sort of rules of thumb. If it takes a smaller number of values and you can deal with it in discrete, that's great. I mean, that's probably the easiest. But if it seems to be taking the data seems to be taking a lot of different values, and you're just breaking your head keeping track of all of them, a continuous model might actually be better. Okay, so with the continuous model, you do histograms and all that. We'll see examples of that a bit later. Okay. Okay, so we're going to close this short lecture with a couple of examples. This is an important skill to have. Suppose somebody shows you a CDF, how to calculate probabilities for events involving the random variable. Okay, it's actually very simple. You don't need to know the deep nuances of these things. You just use the formula, but sometimes you can slip up. You have to be pay careful attention. I would say you should try to sketch the CDF and make sure you clearly understand what type of question is being asked and where it falls, etc. So I've put a whole bunch of calculations. I may not do all of them. What I feel is representative, I'll do. Okay. So here's a whole bunch of probabilities that are being asked here. Maybe some of them are not. Maybe one or two I might add to this. So for instance, you may want to calculate probability. Two more things which may be interesting. Probability that x is greater than let's say -2. Probability that x is greater than or equal to, let's say 3. Okay, why not, right? Let's just add these things. Okay, so I like to sketch. I think sketching is good. Do I have a page for working out? Let me just check. Yeah. Okay, so sketching is quite nice. So let's just sketch it. Okay. So first, it's good to get the range and the ideas. So for x less than -5, it's going to be 0, and then between -5 and 0, it's just 0.2. It's flat 0.2, and notice this is square dot, and this is like this. This is 0.2. Okay. And then at 4, at x equal to 4, it becomes 1, right? So maybe this is not a great scale, but anyway, it's 1 at this point. And between 0.2 and between 0 and 4, it's got a linear rise, right? It's 0.2 plus 0.2x. It's a linear thing. So I know my this thing is going to look like this, right? So you can test it out, right? So x equal to 0 gives you 0.2, x equal to 4 gives you 1, and that's how it looks. Okay, so there is a jump here, and the jump is of height 0.2. Okay, and there is no jump other than that, and then this is 1, this is 4. Okay, so that's your CDF. Okay, so sketching is quite useful. Once you sketch, it's very easy. So probability that x is less than -3. Okay, so the first calculation itself is a bit difficult. So let's start with x less than or equal to -3. Okay, so we'll start with the easiest one. Probability that x is less than or equal to -3 is simply f of -3, and that is 0.2, isn't it? F of -3 is 0.2. It's very easy. So what about probability that x equal to -3? Okay, at x equal to -3, f is continuous, right? It's staying the same, so this is 0. Okay, so once you see that this is 0, you can quickly find what's probability that x is strictly less than -3, which will also be 0.2. It's 0.2 minus 0, which is 0.2. Okay, so this is how you do these calculations. Hopefully it's clear to you. The next question asks you for -3 less than x less than -1. Okay, so this is going to be f of -1 minus f of -3. So that's 0.2 minus 0.2, it's 0, right? So again, -3 to -1, f is continuous and it stays flat, right? So it's going to be 0. There's no change here. What about -1 to 1? Okay, the formula doesn't change, right? F of 1 minus f of -1. So f of 1, if you put 1 here, you're going to get 0.4. F of -1 is 0.2. So it's 0.4 minus 0.2, 0.2. So notice how the answer comes out very cleanly. It's just using the formula, but you have to be careful when you do it and not get misled by what's going on. Okay, so let's look at let's look at the other cases. So maybe I'll use the other page for it. Probability that x is greater than -2. Okay, so for this it's best to do 1 minus probability that x is less than or equal to -2, and that is just 1 minus f of minus 2, that's 1 minus 0.2, that's 0.8. Okay, so you see how I got that calculation? It's quite easy, right? X greater than minus 2 is 1 minus probability that x is less than or equal to minus 2, and that is just the CDF, direct definition of the CDF. Okay, so the next question is asking for probability that x is greater than or equal to 3. See, notice at x equal to 3, it's continuous. Okay, so probability that x equal to 3 is 0, so I might as well write it as probability that x is greater than 3, and that would be 1 minus probability that x is less than or equal to 3. So that's 1 minus f of 3, and f of 3, if you put x equal to 3, you get 0.8. So 1 minus 0.8, that's 0.2. Okay. So this is how you do it. You just have to carefully look at every point and do it off. There's one more question that's being asked: is 0 less than or equal to x less than 3? That is just, f of 3 minus f of 0, and that will work out as 0.6 if I'm not wrong. Okay. All right. So the next question that's asked here: is there an x naught for which probability of x equal to x naught is greater than 0? So this is answered by looking for jumps, right? So that jump happens only here. Okay. So probability that x equal to minus 5 equals 0.2. There's no other value that is taken with positive probability except for minus 5. So is x a continuous random variable? Answer is no. Okay, it's not a continuous random variable. Is it a discrete random variable? No, that's also no. It's one of those mixtures, neither discrete nor continuous. Okay. So hopefully this gave you some confidence. Just given a CDF like this, you should have this basic skill of figuring out probabilities for different intervals and values and everything. This is easy, but you have to systematically do it, correctly do. Okay, so here's another example. I'm not going to go into great detail here except for just plotting. Okay, so let me just plot this and maybe answer a few questions, maybe not everything. It's 0 up to minus 5. Then from minus 5 to 0, it goes as a straight line. At minus 5, it's 0, right? At minus 5, it is 0. Okay, that's important to check, right? So if you put minus 5 here, you get minus 0.2 plus 0.2, that goes to 0. At 0, it is 0.2. And it's a straight line. That's interesting, isn't it? Okay, it's a straight line. And then at 4, once again, at 0, it is 0.2. It's continuous again. And then at 4, it becomes 1. Okay, so it goes up like this and stays at 1. Okay, so that's the shape. So it's all continuous. It doesn't jump at all. There's no jump. Okay, it's continuous. So is x a continuous random variable? Answer is yes. Okay, there's no x naught at which probability of x equal to x naught is greater than 0. It's always equal to 0. So your calculations will change a little bit here there. I'm not going to repeat the probability of intervals here. I will leave that as an exercise for you. Hopefully you'll see how to do it. It's just f of identifying the interval carefully, associating it back to the CDF, and you'll be done. Okay. Okay. So that brings me to the end of this lecture. Once again, what did we do here? We looked at the CDF, and every valid CDF we said actually corresponds to a random variable, and the properties or probabilities involving that random variable, for events involving that random variable, can be calculated using the CDF's definition. In particular, there is one special type of CDF. When the CDF is continuous everywhere, that random variable is called a continuous random variable, and this continuous random variable has this odd property that the probability that the random variable equal to a particular value is always 0. The reason is, when you specify it with infinite precision like that, it's not possible for you to associate a non-zero probability there. But if you put a small enough interval, then you'll get a small probability. Okay, intervals have non-zero probability. A particular value with infinite precision has 0 probability, and for continuous random variables. So the continuous and the discrete are two different worlds. Okay, and when you have a continuous CDF, you have a continuous random variable, and its behavior is very different from a discrete random variable. When there are jumps, there is a probability, positive probability with which the random variable takes that value. When there is no jump, it does not take that value with positive probability. Okay, I hope this is good enough, clear enough in some way. I mean, as you keep practicing, the skills you need to practice importantly are given a picture of the CDF, you should be able to calculate probabilities, you should be able to check whether it's a valid CDF or not, you should be able to figure out whether it's a discrete random variable or a continuous random variable or a mixture or things like that. Okay, so what we'll consider from now on are continuous random variables. In particular, how can you do calculations more easily using continuous random variables and special types of continuous random variables. And as I showed you, continuous random variables are invaluable for various modeling scenarios. Okay, thank you very much.